Hello and welcome to this session on turbulence modeling. So this is in line with the lectures that we are having on ANSYS Fluent. Because turbulence is an important part of modeling procedure, therefore we are having a look at it in coordination with the other lectures of ANSYS Fluent. So what I expect from you to have gone through is basic terms and methodologies in CFD. You should be well familiar with fluid mechanics and the CFD equations. And if you are familiar with the user interface of any CFD software, this should suffice to the need that by the end of this lecture you can answer questions regarding what is turbulence and why we have to model instead of resolve the complete turbulence phenomena. And there's a whole list of choice of turbulence models. We'll be looking at them in the course of this presentation. Just to give an overview, we're going to look at some of the definitions of turbulence and see what happens within the turbulent flows. What is the concept of energy cascading, which actually drives our understanding of the turbulent phenomena and helps us to know how we can model it. And this is one of the points where we'll try to answer why we rather prefer to model the turbulence phenomena than resolve it completely. And we'll follow it up with different kinds of approaches by which this turbulent flows can be modeled. Well, turbulence is encountered in almost every walk of life. Whenever there is a flow, it's very hard to encounter a laminar flow. If you are familiar with laminar flow from the fluid mechanics lecture and turbulent flows, so turbulence is actually a flow in which it's highly chaotic. It's a three-dimensional phenomena. It is not a two-dimensional or a one-dimensional phenomena, which means that the curl of the velocity vector, which is del cross v, is non-zero. That is, it has non-zero vorticity, and it actually leads to a lot of enhancement in the heat transfer and transfer of any other property. So all the flow equations, the properties get distributed within the domain quite in an efficient manner actually, if the turbulence is starting off in the flow. So there are some examples like a turbulent flow can be when a jet enters into a stagnant fluid, then it starts interacting with the stagnant fluid and starts becoming turbulent. There can be wake behind cars or objects, blunt bodies, which also cause turbulence. Just to have an idea about the different characteristics of turbulence, so it's a fluid motion in which all the flow dependent variables like velocity, pressure, and any other flow quantity which fluctuate irregularly in space and time. Now, when I say it's irregular, that's very important, that it is an unsteady phenomena. It's a transient phenomena in time, and it is not at all uniform. It's not at all two-dimensional. It is a highly three-dimensional phenomena. So actually speaking, we cannot imagine a CFD simulation of a turbulent flow which is a two-dimensional geometry. It's not simply not possible, or we cannot imagine a steady state turbulent flow simulation. So the question is, why do we nevertheless have 2D analysis? Why do we have steady state analysis at all if the feature turbulence is highly chaotic and highly non-periodic in space and time? Well, the answer is that we have something called modeling, and I'll speak about it, how modeling is approached and what is the reason for modeling, what is the justification for modeling. But still about turbulence, it is a rotational phenomena, so it has del cross V being non-zero, and it's usually encountered and assessed by a number called the Reynolds number, which is a ratio of inertial and viscous force. And when these inertial forces exceed the viscous force by a huge quantity, that's when the different lamella start mixing together. So let's say this is a flow which is laminar, so the different layers or lamella are maintained in the flow, and that's when the Reynolds number is below a specific value, when the inertial forces are still, compared to the viscous forces, not so high, so that the layers are maintained. But once the Reynolds number exceeds that specific value, the layers start mixing together. This mixing can occur because of changes in geometry. It can also be because simply the inertial forces are too high, that the layers start mixing together, and that's when we can say that the turbulence has set in to the problem. So as far as turbulence is concerned, it's a highly unsteady and irregular, non-periodic in space and time kind of a phenomena, and it results in enhanced transport of all flow quantities which are fluctuating in time and space. There is no uniformity in turbulence. So what we ultimately encounter is a large variety of sizes of eddies. So you see very large eddies, you see very small eddies, the larger eddies breaking down into smaller eddies, and the smaller eddies are breaking down further into smaller eddies. And we are going to speak about what is the concept of energy cascading in this regard. But basically, turbulence results in a loss of pressure energy. It basically results in a loss of the flow energy which is driving the flow. It is lost, and therefore the question comes that there are situations when we would like turbulence because it would enhance our heat transfer coefficient, it would enhance the mixing of the different species, but it comes at a cost of the loss of pressure. So we have higher pressure drop, and that's why we have a trade-off here, that we have to ask ourselves whether turbulence is desired or not, whether it's a boon or a bane. Because if turbulence is desired, then we have to pay the cost of the reduced flow pressure. So let's say flow is entering into a piping structure, and we want enhanced turbulence to cause efficient heat transfer. The cost we have to pay is that we have to the duty on the pump, or let's say a compressor which is attached at the beginning of the piping structure, is increased because it has to provide higher pressure to cause the same amount of mass to flow within the domain. So the cost is the pressure drop, which is increased because of turbulence. So what happens in turbulence is, like you can imagine, a particle enters into the domain. It doesn't just go straight away out of the domain, but it spends a lot of time mixing together, interacting with the walls, spending its time together, and it needs energy for this. And the energy that it gets, the fluid particle gets, is from the pressure which is applied at the inlet, and the difference in pressure, that is a pressure drop, which is driving the flow. And this pressure drop is eaten up by the fluid particle in spending more time than required inside the domain. So the residence time does increase, it does increase the amount of mixing inside the flow domain, but the cost we have to pay is the loss in pressure. So just to classify how we approach the turbulent flow in terms of Reynolds number, let's have a look at different kinds of Reynolds numbers. So Reynolds number is defined as the inertial force upon viscous forces, and we are very well familiar with the definition in terms of mathematics. So when the Reynolds number is less than 10 for most of the problems, we have a flow regime called the creeping flow regime. Now in the creeping flow regime, this is where most of the bacteria or sperms, they are moving at this regime. The Reynolds number is quite low, that's why they have to struggle very hard to move even a little bit ahead. But human beings, we don't operate in the creeping flow regime. Our characteristic length scale is quite high, that we are well outside this creeping flow regime, because the struggle in the creeping flow regime is that you have to move very much to move in the forward direction. So it's very hard to exist in the creeping flow regime. But if we go ahead from the creeping flow regime, when the Reynolds number slowly starts increasing, we have the laminar flow regime until the onset of the transitional flow, where the flow is partly laminar and partly turbulent. And then the low turbulence regime starts off, and then it becomes highly turbulent. That's the turbulent flow regime. So the important thing is to determine these Reynolds transition and Reynolds turbulent in most of the cases. In some cases, this 10 is also not a fixed value. We'll see some examples and we'll understand them. So let's have a look at the pictorial representation of a jet which is coming out, and as it comes out of the orifice, you can see some vortex roll up takes place, and these vortices also interact with each other, and as they proceed further into the stagnant fluid, this becomes a fully turbulent flow. Another very important example is flow around a cylinder. It's a two-dimensional view that you can see here, and for a lower Reynolds number, you can operate in the creeping flow, but above this you are slowly entering the laminar flow regime. In the creeping flow regime, the flow sticks entirely to the surface of the cylinder, so there is no flow separation at all. But beyond the creeping flow, in the laminar regime already there is a flow separation. There is a separation bubble formed here, and this separation bubble starts becoming unstable if you increase the Reynolds number beyond a value of something like 30, that the oscillations start occurring. So there's a small push because of which this vortices behind start fluctuating all the way to a turbulent flow regime. As you can see here, it's a very highly non-periodic, it's a non-unsteady and non-periodic phenomena in space and time. So this is another example how turbulence sets in. Let's ask ourselves, when is the flow turbulent? Well, the flow being turbulent is characterized by certain questions that we try to answer. So we try to see first of all whether the Reynolds number is beyond a specific value. So for internal flows, the value of around 2300 is when we say that the flow is becoming turbulent, although this number may vary from problem to problem. So it is defined in terms of a length scale, characteristic length scale, which can differ for different kinds of problems. For external flows along a surface, let's say there's a boundary layer generation which is proceeding further and into the domain, it might happen that beyond 500,000 Reynolds number, the flow starts becoming turbulent. And especially if it's a flow around an obstacle, it becomes turbulent around the 20,000 Reynolds number figure. So these are some of the values which we know from literature. Natural convection problems are to be understood in a different manner though. They are defined in terms of Rayleigh number, Prandtl number, and Grashof number. So Grashof number is the ratio between the Rayleigh and Prandtl number. So if this ratio exceeds the value of 10 to the power 9, then we say that the natural convection phenomena is also becoming turbulent. Most of the time it is not the case. Natural convection is a laminar flow, but as, let's say, the flow proceeds inside a chimney, as it goes up after beyond a point, it might become slightly turbulent as well. The concept of energy cascading is very helpful to understand turbulence phenomena. So in turbulence, what happens is there are larger eddies, and these large structures or larger eddies break down into smaller eddies. They keep on transferring their energy to the smaller eddies, and this keeps on happening until a point where the energy gets completely lost as heat. So this energy cascading picture, which Richardson proposed in 1922, speaks in terms of a length scale, and we'll have a look at this length scale more in detail based on an energy spectrum for turbulence. So we have energy cascade from large scale to the smaller scales. The large scale is where the wavelength, that is the size of the eddies, is small. The large scale is where the wave number of the eddies, that is the inverse of the wavelength or inverse of the length scale of the eddies, is smaller. That is, the wave number is smaller, then we say it's an integral scale. That is the characteristic of the large eddies. In between there is something called the Taylor microscale. So this is where somewhere in between the larger eddies and the smaller eddies, the region lies here, where the turbulence is more or less isotropic. The turbulence is quite mixed together. So this is encountered in highly turbulent flow. And even smaller than this is the Kolmogorov scale. The Kolmogorov scale is where the eddies are quite small, and beyond this it can really get converted into heat energy. So if the eddies break down smaller than this, so this is the highest wave number, and all these numbers, all these length scales and time scales are defined in terms of some terms like turbulence kinetic energy and the turbulence dissipation rate and the kinematic viscosity of the fluid. So now that we know that turbulence is a very complicated phenomena, chaotic, three-dimensional, let's ask ourselves whether we can actually resolve it, whether we can really predict each and every small eddy's size, each and every small eddy's behavior. So basically the Navier-Stokes equations, they describe both laminar and turbulent. There is no special distinction in this case. And if we can actually solve the Navier-Stokes equation exactly, then well, we are done with the problem. We don't have to worry about whether it is laminar or turbulent, but all turbulent flows can also be simulated numerically if I can solve the Navier-Stokes equation. The question is that such direct numerical simulation of the Navier-Stokes equations is quite prohibitive because the size of the cell has to be very small to capture the smallest eddy, and the time, because it's an unsteady phenomena, we have to march in time, we have to do an unsteady simulation, a transient simulation. The time step has to be very small so as to accommodate the behavior of the smallest eddy. So such a kind of analysis in CFD is impossible for real industrial problems, and it's not even so necessary. So as a practical alternative to these hardware limitations, there are some turbulence models which are available. Now these turbulence models, what they do is they don't actually capture each and every small eddy, but they give you the effect of the eddies. They give you the effects in terms of mixing, as I had spoken about it earlier. The turbulence increases the mixing, and turbulence causes more pressure drop. So if I can have a model which can predict the same thing, it will not actually capture all the eddies, but at least that it will tell me what is the extra pressure drop because of turbulence and what is the enhancement in the mixing characteristics. So then we are done with turbulence. So turbulence can be tackled therefore through a modeling approach, because resolving it through direct numerical simulations is quite impossible. Before we start with turbulence, let's have some understanding of turbulence phenomena from the modeling perspective. So, well, turbulence is dissipative in nature, so the kinetic energy of the flow is converted into heat through viscous shear stresses which is existing within a turbulent flow. So when there is no energy supplied, actually my turbulence will eat up all my energy and there will be no flow occurring. So um, so a requirement for a flow to be turbulent is that it should be very random and there should be viscous losses. So there can be sound waves, for example, they are moving around, these are pressure waves, but they don't really cause a significant viscous loss. In that case, we can consider that these losses are cannot be termed as turbulent flows or turbulent quantities. So what we have to be aware of is like turbulence is also continuum phenomena. So the continuum mechanics is still valid. We are operating at Knudsen number much lower than 1. So we are operating in the continuum regime. So the laws of equations of fluid mechanics are still valid. The smallest eddies are still significantly larger than the molecular scale. So we are quite safe as far as capturing the physics with continuum mechanics is concerned. The other important characteristic is turbulence is characterized more by dimensionless numbers like Reynolds number. It's not just say the property viscosity or density, but it's a combination of viscosity, density, the length scale, as well as the velocity scale of the flow. This is what characterizes a flow phenomena to be turbulent or not, and therefore be it liquid or gas, it doesn't really matter so much. In both cases the flow can be turbulent, and most of the dynamics of the turbulence phenomena becomes independent of the properties of fluid, especially if the Reynolds number is quite high. So it's a flow feature independent of the fluid. Just to give you an illustration of a low turbulent regime and a high turbulent regime, relatively lower Reynolds number and higher Reynolds number, you can see at higher Reynolds number it's more isotropic flow. At lower Reynolds number, the flow contains larger structures and lower structures. So this is more difficult to model. This higher Reynolds number flows, it's easier to model. It's easier because of the isotropic nature. And we'll see this more exactly when we look at the turbulence models. Turbulence modeling, we should be also aware of what is the procedure. So the procedure follows the following, that we try to close the system of mean flow equations. We look at what exactly these mean flow equations are, and most of the time for engineering applications we don't need to resolve each and every small eddy. We don't need to have all the flow fluctuations as a function of time and space, but we can try to model them and get the effects in terms of the different quantities like pressure drop and enhancement in the mixing characteristics. The turbulence models also they allow for the calculation of the mean flow quantities without actually resolving it completely to the greatest minutest detail. So there are some advantages, but there are certain things for which we have to be cautious also regarding turbulence models. So turbulence models, they save us a lot of time and work. Computational effort is reduced drastically, and most of the time we only need to know quantities like how it affects the mixing characteristics, how much is the loss in the flow energy, and these quantities are enough for most of the time in our simulations. And it is possible to calculate also some statistical properties such as RMS values still with the turbulence modeling options. But we have to be cautious while dealing with turbulent flow results that they do not actually show the existing flow pattern, because most of the time we look for a steady state flow, although actually turbulence is a chaotic and highly transient phenomena. So it does not actually satisfy the steady state Navier-Stokes equation either. And to be very clear about it, that actually flow never looks that way in the case of turbulence flows. But while this is fine as far as the real picture is concerned, but what we can see is that turbulence models help us at least to approach the problem to a great extent with accuracy as far as predicting the pressure drop and mixing is concerned. And this is the question, how do we model this then? Or what to do with turbulence? So we have already seen that there is a modeling approach and there is a capturing approach. Capturing can be done by direct numerical simulations, but that's out of question for real industrial problems. So we move on to doing a modeling. And modeling is done primarily by two means. One of them is called the time averaging approach. The other one is called the space averaging approach. The time averaging approach further consists of two approaches within them. So turbulence stress calculation approach, which is called the RSM model, Reynolds stress model. So we actually calculate the turbulence stresses which come because of time averaging of the Navier-Stokes equations. I'll speak more about this in detail in a few slides from now. And the other approach is called the eddy viscosity approach. So these are the two primary approaches with which we can do a time averaging of the turbulence modeling approach. The other space averaging approach towards modeling, it helps us to do an averaging of the smallest eddies of our problem, but the larger eddies can still be resolved. So you are doing some kind of direct numerical simulation of the larger eddies, but the smaller eddies, therefore it's called the large eddy simulation, the smaller eddies are being modeled. So this is the space averaging approach. Within the turbulence stress calculation approach, which is the Reynolds stress model RSM, we actually end up solving five equations, five extra transport equations apart from our flow equations, and if required energy equations. We solve five additional equations in two-dimensional problems and seven additional equations in three-dimensional problems. We look at what exactly these equations are. On the other hand, for eddy viscosity approach, there are a variety of options available. The zero equation model, which was the first one which Prandtl introduced, called the Prandtl's mixing length model. The one equation model, typically called the Spalart-Almaraz model, which is used for aerospace applications for external flow dynamics. And the two equation model, which further contains, there are two categories primarily, the K epsilon class of eddy viscosity based time averaging model for turbulence, and the K omega based approach for two equation models within the eddy viscosity approach. The K epsilon basically further contains some categories like standard K epsilon, the RNG K epsilon, which is renormalization group. It's just a modification of the standard model, which accounts for non-isotropic eddy viscosity within the domain, and the realizable K epsilon, which tries to achieve more accuracy for turbulence prediction. And the K omega contains the standard model and the shear stress transport, which is actually a combination of K epsilon and K omega. We'll see what are the advantages and disadvantages of each of them, why therefore this mixture of K epsilon and K omega comes into picture, which is called the SST model or the shear stress transport model. Apart from all these things, there is something else which is a combination of this time averaging approach and the space averaging approach. So large eddy simulations combined together with the time averaging approach, which is called the detached eddy simulation or the DES. So there are some regions in which the RANS or the time averaging is done. There are other regions in which the large eddy simulation is performed. And this is the complete set of turbulence models available in most of the commercial software packages nowadays. And this language which I've used here is primarily what ANSYS CFD products use. And overall, this shows us what turbulence modeling actually aims to do. Let's start looking at the time averaging approach now. So time averaging in terms of turbulence stresses and eddy viscosity approach, two approaches we have, the Reynolds stress model and eddy viscosity approach. Both of them are based on the Reynolds averaged Navier-Stokes equation. We are going to have a look at what exactly this Reynolds averaged Navier-Stokes equations are. So what we start off with saying is that we define the velocity which is fluctuating. As you can see here, the velocity is very fluctuating. There is no actual velocity profile. We define it in terms of a time average, this red line that you can see, a time average velocity and a fluctuating component. So there is an instantaneous velocity which is containing a time averaged component and a fluctuating component. And we tried to implement this definition of instantaneous component in terms of time averaged and fluctuating component, and we implement this into the Navier-Stokes equation. We do a time averaging on both sides, and then many terms just vanish. What is left is this Reynolds stresses, this extra u dash terms, which are fluctuating components in the x and y and z directions, and this constitutes the Reynolds stresses. We'll look at it more in detail in the coming slides now. So the time averaging of the momentum equations, it leads to the elimination of several terms. We'll see how they get eliminated, because the instantaneous velocity is expressed in terms of a time averaged velocity and the fluctuating component. And the fluctuating terms that remain, which are the ones which need to be modeled. We are going to have a look at them, what exactly these are. So this is the complete set of equations, not just the momentum but the continuity, the scalar transport equations, and the three momentum equations. The capital U that you see here is the time averaged quantity, and this small u dash that you can see here, these are the fluctuating components which are left after time averaging is done. And this elimination of some of the terms will be described in the next slide. But this is what is called the Reynolds stresses. Now if you remember, I said there are two approaches to the time averaging approach. One is to actually calculate these Reynolds stresses, and the other approach is to express them in terms of an eddy viscosity times the velocity gradient. So this is the eddy viscosity approach. We're going to have a look at these two approaches. So how exactly this works is because of the following, that the average of the fluctuating component is time average of the fluctuating component is actually 0. So therefore when I do a time averaging on both sides after implementing the instantaneous velocity as a breakdown in terms of the time averaged and the fluctuating component, when I do a further time averaging of the Navier-Stokes equation, many of these fluctuating components which are time averaged vanish away, and what is left are these Reynolds stresses, which is left for us to model. This is called the Reynolds stresses, and these are the extra terms which come up in the Reynolds average Navier-Stokes equation. And this is where the modeling comes into picture. Now if I can actually calculate these Reynolds stresses in two-dimensional or three-dimension, and through some transport equations for each of these stresses, this is called the RSM model, or the Reynolds stress model. And in the other case, if I can express these Reynolds stresses in terms of an eddy viscosity times the gradient of the the time average velocity in each direction. So this is the typical approach that anyway Newton has defined, and Newton's law of viscosity will be applied. In that case, this eddy viscosity times the velocity gradient, this approach is the eddy viscosity approach. The question comes how to calculate this eddy viscosity. So for calculating this eddy viscosity, there are zero equation models, there are one equation model, and there are these two equation models. There are still some more 3 equation and 4 equation models to predict also the transitional modeling which is taking place from laminar to turbulent. So these are additional models which have not been included in this slide, but primarily you can see it in this way, that there are 3 primary approaches of predicting this eddy viscosity, either as a 0 equation model or a 1 equation or a 2 equation model. And 2 equation model is further classified as k epsilon and k omega, which have their further classification in terms of accuracy. So let's have a look at these stress terms that we have. These stress terms in the x, which is actually a tensor quantity. So each of these Reynolds stresses, which are, I mean, it's a tensor quantity as we can see here. So it has xx, xy, xz, and in the y direction and z direction. So this quantity, all that we have on the screen. So these stresses are determined either by actually solving for these 6 extra stress terms and 1 equation for the dissipation rate to close the 6 equations which are defined. So this is a 7 equation Reynolds stress model in 3 dimension. It is computationally very challenging, and it does account for the anisotropic eddy viscosity. So it does not assume constant eddy viscosity, so there is no problem which we encounter in this eddy viscosity approach, which I'll discuss just in a minute. And it is very helpful for predicting the turbulence phenomena in highly swirling flows. The other approach that we have, the turbulence stress, each of these turbulence stresses will be written as an eddy viscosity multiplied by the mean velocity gradient. This is the other approach. So this mean velocity gradient is the time averaged velocity gradient. So this is the only task is how we can predict this mu t, which is the eddy viscosity. So this eddy viscosity can be either expressed in terms of the zero equation algebraic correlation, which Prandtl had proposed, the first mixing length model, which is available in ANSYS Fluent through a text user interface. And the other approach is the one equation model, which is the Spalart-Almaraz model, especially very useful for aerodynamic applications, for external aerodynamic flows around airfoils and others. And still the third approach, which is the two equation model, in which the eddy viscosity is evaluated as a function of terms like k and epsilon or k and omega. So the task is left to solve for this additional k and epsilon equation or k and omega equation. So additional two transport equations have to be solved, and then the eddy viscosity is expressed in terms of these to close the whole turbulence model.